Okay, first, thanks the organizer for having me here. Thanks for everyone for staying. This is an immensely enjoyable workshop. So I'm gonna tell you, I want to share with you a story about my attempt to try to to build a categorical symmetry fluid from anomalous theory without triangle diagram. So this is a work in collaboration with Joe Dawicki at CERN and Nakari Lohisiri, who was in Durham. And this work appeared last year. There's a work that I hope appears 2 months ago, but it hasn't appeared. So, okay, but hopefully soon. And sorry, yeah, oh, thank you. All right, so, uh, I know this is the last talk of the day and everybody will be tired. So I put the picture of this majestically cute pygmy hippo from Thailand. It has nothing to do with the talk whatsoever, but at least it's cute. By the way, feel free to interrupt me at any point. I mean, I'm the only thing stand between. The only thing happens after my talk is dinner, so feel free to interrupt me anytime. All right, so you heard this morning about like this beautiful symphony between like symmetry and hydrodynamics. So essentially, like if you start with some microscopic theory with global symmetry, let's say, okay, there's some operator that generate a transformation, there's a conserved charge and a continuity equation, then okay, then you heat the system up, looking at the late time dynamics and like at large distance. There's a good chance that this will be described by a system of hydrodynamics. So what actually that means, but I should say by hydrodynamics, I mean normal phase hydrodynamics. By that, I mean like you start with your current, express them in terms of the concept density, and okay, try to build in some way and do the gradient expansion order by order. With the transport coefficient, which is the unknown, the coefficient that controlling this expansion d, that determined by microscopic, and there's a good chance that this, like the IR dynamics, which is like macroscopic motions, and also like the correlation functions, of you can obtain from this equation, which is the resulting thing is a diffusion equation. So this is very beautiful. So just you really have to know the global symmetry of the system to determine what happens in the IR. And so the obvious question is, can you do, if this works so well, I mean, can you do more? And people actually try that. So here's a list of like bunches of other symmetry that you can try. You can try to do non-abelian symmetry. You can try to do fracton. You heard a lot about those on Monday. You can try to play with higher form symmetry, like in 3+1 dimension, you get magnetohydrodynamics. In 2+1 dimension, you get dynamics of domain walls or something that looks like elasticity theory. You can also play with anomalous symmetry, and then of course, like one would try the categorical symmetry here. And you heard many of these things from the previous talks today. All right, but I want to emphasize two items on this slide. So first one is the anomalous symmetry. First of all, I have to say anomalous symmetry is super cool. Okay, so what happened is that when you have an anomaly, the usual statement is that the conservation law is violated by when you couple to the external source, and the coefficient of breaking is controlled by this triangle diagram. And then there is a beautiful derivation purely based on macroscopic that when this happens, there is a current, and the number, the U1 current and the momentum current that flow along with the magnetic field and the vorticity. So this is a bit weird, right? Because we know from elementary school that if you have magnetic field line, then electrons or whatever charge under it will just like rotate around it, and that's not flowing. But you can show, like again with purely macroscopic argument. I think this is like Piotra and Son work in 2009. Yeah, but from that there will be a current flowing along these things. And not only that, this is already a weird transport, and it's pretty cool. That the conductivity of basically the amount of current flow along with magnetic field or vorticity are controlled only by thermodynamics, some number, like what not like 2 or 8 or 4 pi, and then the anomaly coefficient which control this diagram. So that this is really amazing. And in some way, the categorical symmetry, which is like essentially what I mean is essentially two groups, and non-invertible symmetry of ABJ anomaly. Like the weird thing that makes this categorical symmetry fluid that already built so far in the last few years, the only thing that makes this one different from the normal fluids, you can trace the origin back to this effect. But so there's a few problem here about like the system. So first of all, the effect that I mentioned so far, like and most of these arguments, these are about perturbative anomaly, namely the one that you can access with this diagram, and those that violate the conservation law like this. And the other problem is that the categorical symmetry fluid that some people cook up earlier, these are only deal with the basically some categorical symmetry that involve continuous parameters. So basically, well, roughly speaking, it's something that you obtain from gauging a theory with this type of anomaly, and then you get like some symmetry structure that are not quite a group. So this is a bit unsatisfying because, and then there's only basically 1 or 2 examples of this type that we can deal with the current method. So maybe there is a better way to, like, we have to think a bit more about what this means for the system to be anomaly, and how do we obtain like a categorical symmetry. So there's no better way to do this than the commuting diagram. So okay, of course the goal, the ultimate goal would be, if somebody tell you a categorical symmetry, like some category data, like RF symbol or Mossberg data or those kind of things. Okay, so if you have all those, it's kind of like you're having a conservation law and for the diffusion. There should be like some procedure to turn those things into hydrodynamic theory. I mean, if that happened, if that could be possible, that would be really amazing. But for the love of God, I have no idea how. So maybe an easier way to do this is to ask like what are many of these categorical symmetry came from, and they came from the procedure basically gauging a theory with anomaly with 12 anomaly. So, but a problem here is that many of the currently known category symmetry, these are like a finite categories, meaning, and they often obtain from gauging a discrete group. But discrete group is like there's no place for that in hydrodynamics, and especially if you have a discrete group, there's no triangle diagram and no violation of validity, and speaking of which, like a theory with 2 plus 1 dimension, there's no anomaly of this type from triangle diagram. So there seems to be a lot of things that missing here. But as I mentioned earlier, then you can, if you know a theory with anomaly, at least perturbative anomaly, you can obtain anomalous hydrodynamics using like various techniques that people develop over the years. So the goal of today is trying to generalize like this direction for the discrete anomaly, basically anomalies that does not have the triangle diagram. And maybe from that point, we can see where discrete anomaly enters anomalous hydrodynamic, and maybe from there we can do the gauging procedure, and maybe we get like a more general versions of how to get the category of hydrodynamics. Is there any questions about motivation so far, by the way? Yes, Piotr. Yeah, that's a good question. I have no idea. But usually, usually for a category that describes the CFT, you have to know like this thing called like R and F symbol, basically how it's braid and how if you have 3 anyons or 3 particles, like how would you change the order of them fusing to each other, and how do they like twist around each other's? So that's like the one of the picture, one of the data that classifies CFT. The bulk theory that boundary is a CFT of rational field, conformal field theory. There are more, and then yeah. All right, then if this is Andy, when did I start the talk? Andy, 10 minutes ago. Okay. All right. Okay. So then you could ask like whether would this program could possibly lead to anything interesting. So the obvious objection to this, like why this might not be a good idea, is okay. Maybe the IREFT is just a decoupled hydrodynamics and a topological field theory. But this is very likely that okay, there's some whatever happened to the category, it's just captured by separate TQFT, and hydrodynamic is just the usual stuff. So I think this is probably what happened in most cases. What will happen in most cases, I have no idea why. But then okay, I could also ask back. Then okay, but are you sure that it will always be decoupled? Can they not really talk to each other? And then there's no criteria why this cannot happen. The other thing is people will say, well, okay, at high temperature, everything should be classical, and this categorical symmetry, these are like kind of like something that has to do with anion fusing each other and all these things. So maybe this is like a genuine quantum, but so you shouldn't see it in classical system. And also, you would say that a discrete charge is not extensive, meaning that it will be washed away when you take the thermodynamic limits. And the usual game is that when you say that set n symmetry is something like you explicitly break U1 symmetry down to Cn, and you just throw it away from the construction of hydrodynamics. So just if some U1 symmetry is broken by ABJ anomaly, usually people just throw it away. So okay, but maybe there is another hint that this could work, and that there will be something that talk between these two sectors. So the example is the anomalous Hall conductivity, or basically a theory that lives on the edge of topological insulator. We know that this is a massless Dirac fermion, and massless Dirac fermion has something called parity anomaly. And in that case, like the edge of the topological phase, this one has an anomalous Hall conductivity, which basically you insert the current, insert electric field in this direction, and there's a current flowing in the perpendicular direction with the quantized Hall conductivity, or actually half quantized. So maybe it's not so hopeless that maybe there's something similar to this. That and clearly this is in this setup is the boundary theory is in 2+1 dimension. So clearly there's no triangle diagram and no usual perturbative anomaly, and yet there's still something that you can see in the transport. So maybe something like this can be generalized. So here's the goal, the real goal of the plan. So I want to show how the anomalous transformation of the partition function happens without triangle diagram. And by the way, okay, sorry, too late. But you can clearly see that I'm gonna talk about hydrodynamics, which means that effectively I'm a plumber. So please be kind with me with the mathematical details. With that in mind, I want to talk about a way to figure out anomalous transformation of partition function with something called the body subgroup. This is supposed to be funny, but okay. And then a procedure of how to figure out the effect of this anomaly in the thermal equilibrium. For expert, this is what the procedure is called, like find a mapping torus that is compatible with the thermal equilibrium. And then I will show you explicit example of like a new transport of anomaly. One of them was known for since 82, before even I was born, and then the new example of new anomaly that we found last year. And then, okay, I would discuss about implications of what this means in hydrodynamics. So basically, the punchline is that even without triangle diagram, you will still see the effect like a chiromagnetic effect, which is a current flowing along magnetic field line and their cousins. So let me tell you about what actually what is an anomaly. So the anomaly is what happened when you have some theory with some symmetry group G, with you compute the partition function, couple them to source, and then you realize that by doing some transformation of the background field, sometimes the partition function change by some phase ambiguity. So this is the usual way you say this, but the another way to see this effect is that you say that this theory, this phase ambiguity, you attribute this to something called the invertible topological field theory in one higher dimension. This is like a name that mathematician call SPT phase. If you don't like invertible, just think of your favorite SPT or classical Chern-Simons. This works in the same way. So you can show that your anomalous partition function, where this your theory on X is a boundary of Y, or some Y in higher dimension, that the partition function is factorized in terms of the part that is invariant and the part that is not invariant, and depends on the bulk. So how this is related to the usual story is that when you attach this theory, the original one, with some SPT phase, it becomes invariant, but depends on the extension to the bulk. So for example, this piece, your theory living on X, and the phase attributed to a theory on Y, when you couple them to another SPT phase, they glue together and combine into a closed manifold. And for those of you who know the TQFT axiom, then a TQFT on a closed manifold is always a C number. So now you can try to compute the phase ambiguity using this technology. So essentially, I will do some gauge transformation. Essentially, imagine I start with a theory over here, and then I slowly stretching it, or do some transformation with it, that it turned from A here to AG over there. And there's a procedure called like a cutting and gluing, or in this case, mostly invertibility. That what happened is that when you have one over partition function, you can turn the denominator to the numerator and just basically flip the orientation of this guy to this guy. So this guy over here. Alexi, where did you get your stick, normal stick? You don't know? Okay. Oh, it's yours. I'm sorry, then that's fine. I'm sure. Okay. I was just thinking that it would probably be more convenient, but okay. So and then one way you can view this thing is that, okay, now you have like this like sausage or something shape, then you can imagine. Thank you so much. Okay. Now you can imagine take these two ends, pull them around and glue them together to form like kind of like a torus. The other way to say this is that once because the end point here is like smooth and this is a point, you can always put them together and squish it a bit. So effectively it's kind of like you take this part, drag it around, and then glue them back together. So this is a configuration called a mapping torus, and just to make it to something that you're familiar with, let's say your theory is on 2 dimension, your invertible theory is just the usual Chern-Simon term, and your transformation is just stretching A to transform it by the background gauge transformation. And then you run through this procedure, and what you're going to get is a familiar phase ambiguity of this kind. So an obvious thing is that if F is equal to 0, then the invertible theory on the mapping torus is clearly 0 from here. And in general, so you have to activate some kind of source, in this case F, and the particular transformation from A to AG, so that the invertible theory on the torus is not equal to 1. All right, so what kind of invertible theory that I'm interested in? So I will be talking about a theory that made out of the chiral fermion in 3+1 dimension, at finite temperature, relativistic if possible. if you're being extremely careful, so then the usual game is that okay, the theory or SPT phase that capture the anomaly of chiral fermion is the usual Chern-Simons. But if we really careful, that it's not quite Chern-Simon term, but some object called APS eta invariant, which defined by the sign of the eigenvalue and do the regulated sum. Essentially, this is like some argument, like an argument of the determinant of the Dirac operator. So you can compute this always. I mean, just diagonalize Dirac operator, find all eigenvalues, take all the sign, do regulated sum. Some people claim that they can do this in one afternoon, but I have no idea how. So you can, and you will get some number, which probably doesn't tell you much. But it has a neat property called APS index theorem, which can be activated if y is equal to, if your theory on y here is a boundary of something else. And the relation is the following, that the 2 minus 2 pi I of eta invariant is related to the index density, which is roughly for 4 dimension would be trace R with R and plus F with F. If it's 6 dimension, is FQ plus F with trace RR, and then those kind of things. And so you can kind of see that if I take W to be the, let's say, some disk that covering Y, then this thing can be written in terms of some sort of like Chern-Simon term, but maybe with some number that pop out of it. But I think the important part that I want to say, which is probably the key that make this whole story work, is that eta invariant can still be non-trivial, even if this thing is non-zero. And you could ask, okay, how is it possible? Clearly, this is an equal size, so how can this be non-zero? How can this be non-zero when this thing is zero? And the issue is, if you cannot possibly find the extension from y, this y to w, in such a way that you can extend the manifold y here to w that keep all the spin structure and the fiber bundle or the gauge field structure. If you cannot do that, if you cannot find the extension from y to w, then this equation doesn't make any sense. And then eta invariant can be non-zero even though this thing is zero. Yes, sir.
What's like the simplest example where you can't find such a W given a Y and all the things on it?
So the simplest example would be if I have a theory on a point. A point is not a boundary of anything. A 2-point is a boundary of a line, but a point is not.
Is there any other examples?
I think the other example is, I think for the fermion with periodic boundary condition on 1 + 1 dimension, this cannot be shrink to, I think that this is the one. Yeah, you cannot extend it to a disk. It's not a boundary of fermion on the disk. Maybe another example. If I have a theory, an annulus with, so it has 2 circle boundary. One of them has a fermion in periodic boundary condition. The other one is in periodic boundary condition. There's no way that I can fill in things in between that preserve the spin structure. The problem mostly came from spin structure. So okay, so the tool that the technical way or the shortened version of this mathematical statement is that if the space Y here and the spin structure and the bundle are now Borden, if they are, you can only use this formula if the manifold and the G and the fiber bundle and the spin structure are now Borden. So what is this word, Bordism? So suppose you have like some manifold M and N, again equipped with spin structure. I keep forgetting to use this, with spin structure and the principal G bundle with basically gauge field. And if they are connected by some one-dimensional higher manifold, then we say that M and N are Borden, and they belong to the same equivalent class. And this object called body subgroup is counted basically a class of a manifold that are not that cannot be connected in this way. For example, if and it denoted in this way. So like the spin here denotes spin structure. This D here denotes the dimension of this guy. And BG, okay, you don't need to know this, but if your group symmetry is G, then this thing is BG. So suppose somebody computed this thing for you, or you compute it yourself, and you get that it is isomorphic to the Z2. What does this mean? So this means that there are two classes of manifold, like M, that cannot possibly be connected in this way. And one of them, so one clear choice of the manifold is at a point. So basically imagine that, oh God. Imagine here that this N is nothing. Then this means that the M is Borden to a point, and so essentially the only boundary of this W is M. But if it's not, if it is Z2 here, it means that there is a class of manifold that cannot possibly be connected to a point, and it meaning that M here, M in M1 in this non-trivial class cannot be connected to a point, and it has to be connected to something else. And you cannot think of it as a boundary of something. Like for example, like the example of a single point, or the case of an annulus with opposite spin structure. And it also tells you the information that the eta invariant, it turns out to be, it was shown, I think, in the paper by Fried and Hopkins, that the eta invariant in the case where the index density is 0, it is a body sub-invariant, meaning that computing this will tell you that, okay, there's a class of manifold M0 where eta invariant is 0 mod 1, and the other one is twice of the original one is go back to the origin to the eta invariant of the previous class mod 1. What this meant to say is that there is also one class of the manifold M where if you compute eta invariant on it, you just get 0 mod 1, and the other one you get 1/2 mod 1, which is reflecting this C2 nature of the body subgroup. So then we would like to ask whether can you see the effect of this anomaly in thermal equilibrium? And then the reason for that is the following. So there's some hidden assumption that in hydrodynamics, your theory are in the local equilibrium, or at the very least, before you perturb it or anything, it should be in equilibrium configuration. So if the anomaly theory can be, well, if we want to describe hydrodynamic theory, at the very least, it should capture the equilibrium sector of the theory, basically when you put them on the thermal cycle. So the game here is that you put your theory of X by your few theory leaves on S1 cross M, or some vibration, essentially, and you write the metric in this Kaluza-Klein coordinate. This is a metric of the spatial direction. This is like a boost parameter. This is a size of the thermal cycle. And you write the gauge field in time component and a spatial component. And then the object we're interested in would be, again, object that many people today have been talking about, the thermal partition function with the defect with symmetry operator inserted. So if you can build a mapping torus out of the transformation from X to A, where X and X prime has the same temperature, then, and if this thermal partition function describe your anomalous theory, then the ratio of the two partition function must be equal to the invertible theory evaluated on the mapping torus. Now the question is that, can you possibly find a mapping torus that activated this invertible theory? In other words, would when putting the theory in thermal equilibrium, would that still be an anomalous transformation? So if it does, then it means that the anomaly enters in thermal equilibrium, and therefore, if it's entering thermal equilibrium, it should enter in the hydrodynamic regime as well. I should say that maybe this thing does not exist, or at least I know there's a few examples where I couldn't find like what these things are that activate the invertible theory. And let's give some examples. So these mapping torus can be pretty wide sometimes. So for example, in the case where my theory is in two space-time dimension, and my group is SAT2. Somehow, for some reason, you compute the spin bodysum group over here, and you get that this is the number SAT8. So what this means is that there is a manifold, possibly mapping torus, that when you compute the eta, it gives you 1/8. And that mapping torus is the following. So again, I put the theory, my 2D theory on torus over here. I inserted the C2 holonomy around one cycle, and then I extrapolate it. And then I transform it with the T transformation in the SR2 set of the diffeomorphism group of the torus, and then I glue them together. So this is like I have a torus, and I slowly transform it, do the T transformation, and then glue them back together, twist it around, and glue it. So if you compute eta invariant on this thing, then you're gonna get 1/8, which is the generator of the bodysum group. Another example is if your theory is in 4 dimension, 4 Euclidean dimension, and your symmetry is SU2, then you compute the bodysum group, the 5th bodysum group, which is now mapping toruses in 5 dimension, and you get SAT2. So it turns out that this configuration is that you start with a theory on S1 cross S3. You wrap the C2 holonomy, which is a center of the SU2 around one of the circle or around the thermocycle. You extend it over here to on one side and the other side, and you connected these two with the G transformation in a non-trivial pi3. And this will result in eta equal to 1/2. Again, as I say, like this doesn't always work. So like for example, in D+1 equal to 3, so two spatial dimension. If your group is U1 and the semi-direct product with time reversal, which mess with the orientation, it turns out that the object that you have to compute is like this weird thing, which is isomorphic to the mod 16. And the point is that the mapping torus here is RP4, which activated this term. And it was computed, but people found this many. How do I go back to full screen? Control L. I think it should be fine. Okay, and so the mapping torus can be like this. Let's say RP4, and for I guess for obvious reason, I have no idea how to turn a theory with circle cross something into RP4. So this is possible, but there's also many cases where it works. So let me try to step back a bit to a bigger picture. So let's say if you want to find a hydrodynamic of this type of anomaly, then what do you have to do? So the first obvious thing is that, okay, if it's this anomaly, what characterizes it? So you should know your invertible theory. But if you don't, or if your invertible theory happens to be eta invariant, then find the bodysum group. Now, this is the first step, which sounds horrible, but it turns out that many people have computed this, and so you can look at this paper, or the paper of the two of my collaborators. So it turns out people computed this. They put them in physics paper, and if you kind of like have to remember who knows how to compute these things, or where to find it, and then you can easily look it up. And then from that, then you try to find a mapping torus that built from S1 cross M in such a way that it activates the invertible theory. And if possible, it should be in such a way that it generates the Bodism group, so that the eta invariant on the mapping torus is the smallest that is allowed by Bodism group, like let's say 1/2, 1/16, or 1/8 that I pointed out earlier. There's a neat trick. I should point it out. There's a neat trick to compute the eta invariant by embedded them in the group, the larger group with only perturbative anomaly. So this is like this method was out since '84, and then there's a revival version in the Bodism group version by Nakarin and Joe. Okay, so now you know how partition function of an anomalous theory transform. Then whatever effective theory you build, it had to transform in such a way that it match that transformation. And a way to basically build the EFT for the log of partition function is you start with these variables of metric and the gauge field in thermal equilibrium, and you slowly use like either this guy or this guy, this guy, this guy or this guy, and start building them into a local effective action. And then the point is, if you don't have any anomaly, you combine them in such a way that it is invariant under all diffeomorphism and the U1. But now, because we want something that transform, particularly in this specific way, you allow for non-invariant term, but you should tune the coefficient in such a way that it produces exactly this transformation. So and the final step, which is kind of obvious, is that now you got effective action for log set, and then vary that with respect to the metric and gauge field and get the strategy tensor and the currents. I have 7 minutes. I have like 3 slides left, I think, so that should be okay. All right, so okay, let me go through one example. So this is a new Bodism group computation that Nakarin and Joe found. Oh, sorry, I should say there's another way to compute the Bodism group. So you find someone who know how to compute it, and talk to them. Like Nakarin is computing Bodism group for breakfast for some reason. So okay, but he computed this, and we found that actually this is a mistake. Oh no, this is a mistake. This should be 4. This should be 5. This should be 5, and this is at 4. So what the mapping torus for this configuration is basically you put the theory on the sphere cross T2, and you place the magnetic flux. One, you need a magnetic flux over here. Put C2 holonomy over here, and then do the SL2 set, the T in SL2 set twist, and then compute eta invariant on that. Then you get 1/4. So now you have to build an EFT out of this guy that when you place them on this configuration with C2 holonomy, one background monopole inside SAT2, it transformed like this. And this is the SL2 set transformation. So it turns out that this is quite easy. The term that is responsible for this is this. So this is the 3 spatial manifold, because I'm in the high temperature phase. You can imagine I wrap up, I compactify the time direction. So this is the Kaluza-Klein gauge view representing the boost, and this is the spatial component of the gauge view. And the coefficient in front is done in such a way that it matched this 1/4. I should point it out that there's this integer over here, which I don't know how to remove. But the point is that there has to be this fraction 1/4. And these one are not controlled, but these one are fixed, but in order to capture this transformation. Now you vary the partition function, and then you get the current and the momentum, which looks like this. So what it is telling you is that there's a coefficient. Well, let's say for some reason I can take this out, this integer to be 0. Then there is a current that flow with the transport coefficient being 1/8 of temperature square. and it has to be this form up to addition of the integer when I add the magnetic field. And similarly to when I stir the system with vorticity in this direction, there will be current going in along the same direction of vorticity. Again, you can play the same game for the SL2. The SU2 in 4 dimension. The free body subgroup is set to, as I pointed out earlier. So the game is that when you place a theory on S3 cross S1, it's set to center holonomy around around the thermal cycle, and you do the transformation with odd degree of G in pi 3, then partition function is shifted by 1/2. And this is quite easy to find, and what you have to do is to add the fractional Chern-Simons built out of the spatial component of the gauge field. And once you do that, then you get the current when basically the non-abelian current that appears when you insert vorticity, momentum current appear when you insert vorticity, or SU2 magnetic field. With the coefficient, again, fixed by thermodynamic variables, some number, and this isospin J, and some number which I cannot determine. Yes?
Question. So this M in this context is S3 times S1 beta, or you integrate over M in the bottom line?
Yes, sorry, M here is S3. Yeah.
Just S3?
Yeah.
Okay, thank you.
Well, I mean, in principle, it can be any M, but what I'm saying is that when I place it to be S3, it has to transform in this way.
So is this integer related to some counter term that you can shift or not?
Yes. So in principle, I think if I do it in microscopic computation, depending on the scheme, I can generate this term. But I'm not I haven't managed to. I think in the microscopic computation that I did myself, I get like exactly like in this case I get exactly 1/4.
Because if it's a counter term, then you could turn it on even in absence of an anomaly.
Yeah, so this is what I'm saying. I'm not entirely sure like whether this is like some counter term that generate. I couldn't find it. But I think the law is that you probably can remove this thing from by your procedure, but this one is a fractional, so you cannot possibly remove it. Okay, so I mean this is it. And I have 2 slides left. Andy, how many minutes I have used? I have 1 or 2 left. Okay, so then can I have maybe 1 or 2 minutes more to finish this? So, okay, what I'm trying to say is that there are anomaly-induced transport similar to this paramagnetic effect or vortical effect. Conductivity are fixed by thermodynamic variables and a fractional number, even without parity and even without triangle diagram. So, and I hope this is comprehensible, that there's a recipe of how to extract the transport coefficient for a large class of theory with global anomalies. Actually, in fact, because we have this recipe, we can do this for all possible classical symbolic group. And it turns out that only USP2N family has half-integer transport coefficients in 4 dimension. So I have to admit something, that this is not complete. So we don't know what to do when some of the symmetry, like time-reversal symmetry, when it mess up with the orientation, like when you get like these Stiefel-Whitney class for a new SU2 anomaly. So we don't know how to do that. And the other thing is that finding body subgroup turns out to be the easier part. The real pain is to find a mapping torus, because there's no real principle of how to find it. And I assume that the normal phase hydrodynamic exists, and that its degree of freedom capture all the anomaly. This may not be the case in some case, but we weren't able to find a sharp condition for that. And also, like by the current TQ of T, we can only do this in Euclidean theory, basically in a thermal equilibrium. I don't know how to do it in a mixed state or in a real-time setup. And maybe there's some constraint that we are missing. And the other thing is that, well, okay, there's a transport like this, but the fact that you have to insert like some C2 holonomy, maybe this is not really easily to do in real, or like non-abelian magnetic field. Maybe this is not something that you can easily do in experiment, but you know, it would be nice if someone can. So let me summarize. I think I used up my time, but let me try to summarize with this. So I mean, we know that now there's a lot of progress trying to understand the categorical symmetry. There's new symmetry happens, I think, on a weekly basis. And a lot of them you cannot understand it from gauging anomalous theory. And we already know quite a lot about SPT phase and global anomaly. There's a recipe of how to extracting the transport phenomena from a theory with perturbative anomaly. And I think like hopefully the thing that we presented here will hopefully expand the scope, that you don't really need triangle diagram to have the anomaly induced transport. And maybe the nice thing is that because now the anomalous hydrodynamic of this type depends on the discrete gauge field or discrete holonomy, maybe by doing the discrete gauging, maybe you will get something interesting. But maybe that's a question for the future. And that's it for me. Thank you very much. Oh. Who was the first one? Do you guys have to eat?
Hi, good. Thanks for the great talk. My question is about literally the last step, where I guess entire dynamical sort of content was there, right? Previous part was like how to understand anomaly, global anomalies per se, right? How to compute that, how to classify it about eta invariant and so on. So the last part was basically how to think about anomaly matching given this anomaly, which is a global type. And if it is a spontaneous broken, we sort of have a pretty good systematic procedure, which is basically constructing generalized Weisman-Witten term. And this can be repeated also for generalized symmetry or categorical symmetries, I believe. Now, what I'm sort of confused is that
it's why didn't I do that?
I'm sorry.
It is the question is that it's why didn't I do that?
Basically, my question is, since you haven't specified the A, you know, what is the degree of freedom that you are taking as a description of a thermodynamic limit? And B, since you didn't specify whether you assume symmetry is spontaneous broken or not, so I couldn't figure out whether you're actually taking the path of Weisman-Witten term or you're asking a more dynamical question. What is the spectrum of degree of freedom you need? What are the interactions you need to sort of reproduce the anomaly you see? So can you sort of comment and clarify, at least help me navigate
Good.
where
So
I am?
I assume that these things are in a normal phase. This is a high temperature phase where no symmetry is spontaneously broken.
Not broken or broken?
Not, well, I mean, modulo like these strong weak symmetry breaking that Andy talked about this morning.
Okay.
I assume in a conventional sense, in equilibrium, no symmetry is spontaneously broken, except maybe boost.
Okay.
Because I'm in finite temperature.
Okay.
So you can think of this configuration as a spontaneously effective theory for spontaneously broken boost symmetry, but nothing else.
Okay.
So that is possible.
All right.
I think the truth is we also tried the Nekura construction of the generalized Weisman-Witten.
Right.
There's some hiccup that I'm not entirely sure how to resolve mathematical or technical question.
Right.
But so what I'm trying to do here is that so you can think of these parameter. I have a partition function that depends on the background field, which I assume to be local, and I have the basically background field data that transform respect to equilibrium. I want to build all of these in such a way that it captures the transformation, and that's it.
Okay, then my
So
question
this is not like a Goldstone theorem.
Right. Okay, thanks. That clarifies at least the one point. So now I know I'm on this side from my very subjective categorization. Then the question is uniqueness of the anomaly matching term you have, right? Which is important question now. So because even for discrete symmetries, anomaly can be matched either by gapless mode or sometimes it can be matched by symmetry preserving TQFT.
Yeah.
And I believe that second kind, we are still very much moving on to see what are the possible theorems applied to this. There are a few examples that is developed Witten and other people.
Like Smith isomorphism and that kind
Right,
of
and
stuff.
Clay Cordova and then and so on. So there are people who have done it. So, but since I didn't hear anything about like spectrum of a gapless mode, are you assuming there's no gapless mode in this game?
No, there's no gapless mode. Everything can be integrated out, and except like the concept charge.
I see. So your game is really understanding what will be the symmetry preserving TQFT that reproduces anomaly.
Yeah. So let me put it this way: like if I the question is that if I have a theory in the most theorem that I think I remember
Mhm.
that you mentioned, these are at 0 temperature. What my question is that what happened at high temperature?
Right.
Can you still see this effect there?
Right.
And what kind of background field you have to turn on in order to see it?
Okay, good.
Yeah.
That helps. Thanks. Thanks a lot.
I had a question about the last step on the last slide, this gauging step.
Like, oh, sorry. This one?
Yeah, that gauging. So would this be gauging a discrete symmetry? Is that what you are envisioning?
I think that's what I have in mind, yeah.
Okay.
But,
Well, why should I expect usually when I think of hydrodynamics, I'm thinking of it capturing local physics. But discrete gauging kind of keeps local physics invariant and just messes with global physics. So why should that hydro theory be any different than the hydro theory before discrete gauging?
well, so if you talk about like the normal intuition is that the hydrodynamic degree of freedom, the hydrodynamic theory doesn't care anything about discrete symmetry, modulo CPT. But in this case, it's already care. So if you turn on the holonomy, you have like non-trivial transport. If not, then there's nothing. So it is kind of already sensitive to the discrete symmetry. And the question is that, okay, if you gauge the C2, would you get something interesting or maybe not? So but essentially, I don't know whether what happened if you do the discrete gauging, what you would get. Maybe it's trivial, maybe it's not.
Okay, yeah, this usually I think discrete gauging doesn't change any local physics. Yeah, so maybe it would be the hydro theory would be different if you inserted defects or something. I see. Okay, thanks.
The other way to say this is that this C2 holonomy that you have to add, you can think of this as like inserting a codimension 1 C2 operator everywhere on the spatial slice, and maybe on this basically on this the center defect symmetry operator, maybe there's something that could be interesting. But I mean,
can you go back to
yep.
there? So is this last expression telling us that you are writing the anomaly as a local term in the partition function?
This one?
Yeah.
Yeah, sure. Why not?
You should be able to remove it.
Um,
Anomaly in the ordinary case, anomaly is not local in
well, so
local in
I
high
think
dimensions, but not in-
what happened is that if there's no j here and or j is integer, then yes, I can. This is I can remove it by a local counter term. But now, let's say if I have a theory, a fermion in isospin 1/2, then this is like a half Chern-Simon term. There's no way I can remove it by the local counter term, if this is allowed in this procedure in the first place. I think that the important thing here is that that's why I say that there's some integer here, which I don't know how to determine, but the fractional part is definitely going to be there. This is a signature of this type of anomaly. Thank you.